Hey guys, up until now we've seen that we can use calculus and integrals to find areas between two curves. If you think about it though, that problem is a two-dimensional problem and we should be able to extend what we've done in some way to more than two dimensions. So if we're living in the world of three dimensions, instead of finding the area, we'd be thinking about how to find volumes of solids. Now, there's a general volume problem which is addressed in multivariable calculus. But in this class, what we're going to be able to do is find one particular volume, and that's finding the volume of a solid of revolution. So we're going to find the volume of a solid of revolution. So what do I mean by that? Well, let me just take some function, so this is f of x, and I can rotate it around. So imagine rotating it around the x-axis. So if I do that, and I take a cross-section, of it, it'll look something like this. Well, now let me imagine this rotation so that I get this three-dimensional figure. So it's kind of like a funnel or a vase. So this is the type of solid that we're going to be studying. So we're going to be rotating some function about some axis. So how do we find this volume? Well, again, when we were looking in two dimensions, we took the ith rectangle, we added those guys up as for an approximation. Then we took the limit as the number of rectangles approached infinity, and we added up all those areas in quotes. Well, if I rotate this, I'm no longer going to have ith rectangles, but instead I'm going to have ith cylinders. So hopefully you can see that with my artistic rendition of a cylinder. So let's take a look at this then. So we want to add up my n cylinders, or add up the volumes of the n cylinders. So how do I get the volume of a cylinder? Well, what I'll need to do is I'll need to get the height of the cylinder times the area of the top of the cylinder. That'll be a way to approximate it. So you may remember the formula for the volume of a cylinder being pi r squared h. So this is the h in this case. And again, I'm stacking them this way, and I'm going to add more and more of them. So this distance is our good friend delta h. Delta x. And then to get the area of the top, my pi r squared piece, pi r squared, well, I need to know what the radius is. So if you think about it, that radius is just going to be the height of the function at that point, namely f of x sub I. So what I'm doing then, again, is I'm taking pi r squared h, and I'm doing that with n cylinders this way, and then I'll take the limit as n approaches infinity. But we then recognize this sum as the integral from, let me call this a and call this b over here, so in terms of the x-axis, I'm going to integrate from a to b pi f of x squared dx. And this is the formula that we'll then be able to use whenever we're rotating a function around a given axis. So let's do some examples with this. And I'm going to leave this guy, let me put this guy up here because we will refer back to it. Throughout the lecture. As one example, let's use this process to find the volume of a sphere. So you might know that the volume of a sphere is 4/3 pi r cubed. Let's actually use calculus to derive this. So let's first draw a picture. And I need to draw a sphere in the context of this problem, thinking of it as a solid of revolution. So what I'm going to do is I'm going to take this function So what is this function? Well, let's see. X squared plus y squared equals r squared would give me the full circle. So that y squared is r squared minus x squared, or that y is the positive square root of r squared minus x squared. So that's what this function is. Then I'm just going to rotate it around. And what I'll do is I'll then get a full circle. In fact, the circle in terms of the cross section, but I'll get the full sphere when all is said and done, rotating around this way. So I'll once again have my cylinders, a little bit of artistic license there. And we now see that the thing that we need to integrate is, well, let's see, my x's are going from minus r to r. Pi times r squared, where r is the ith radius. Because again, what we're doing is we're stacking them this way, so the radius is going to change as I move through this thing. You can think of it as stacking pancakes this way. So what is that radius for a given x? Well, this is what the radius is going to be. It's going to be the square root of r squared minus x sub I squared. But once again, putting this into integral form, you get the square root of r squared minus x squared. That's my f of x. And then I want to square that. So that's the integral that I want to compute. I would recommend pausing the video and giving this integral a shot. All right, so hopefully you said, oh, that's the same thing as the integral from minus r to r. Pi times, well, squaring a square root gives me r squared minus x squared dx. Then I could pull out that constant. Integrating r squared, where r squared is just a constant, so it's just r squared times x. This becomes minus x cubed over 3. And then I can integrate from minus r to r. But actually, I'm going to make life easier for myself. I'm going to integrate from 0 to r. From 0 to r, so I'll do it for this half, and then just double the answer. So I'm using the symmetry of the picture just to make my integral easier, so I don't have to plug in a negative r. Okay, so let's plug in our values. We get 2 pi times r squared times r minus r cubed over 3 minus 0, 0, 0, so minus 0. So we get 2 pi times r cubed minus r cubed over 3, 3r cubed over 3 minus r cubed over 3 is 2r cubed over 3, and we get 4/3 pi r cubed. Beautiful. We have just derived the volume formula for a sphere using calculus. All right, so let's look at some other examples. So as another example, let's find the volume of a solid generated by rotating y equals the square root of x about the x-axis as x ranges from 0 to 1. So I invite you to pause the video at this point, and all I want you to do is set up the integral. That's all we're going to be doing for the next couple of examples, but give it a shot. Right, so hopefully what you did is you first sketched this. We have the square root of x. X is going from 0 to 1. And we're rotating about the x-axis. On the other side, it'll look like this. And we have this bowl type shape. Again, I'm going to draw in my typical cylinder, a little bit of artistic license. And then what I'm going to do is I'm going to add up these cylinders as x goes from 0 to 1. Pi times the radius squared dx. So I always write out the skeleton of the integral first, and then I think about the piece that requires the most thought. So in this case, it's not too bad, because the radius for a given x is just going to be the square root of x. So this will go in here, and that is the integral representing the volume of this. All right, let's do a couple more examples that are a little bit more interesting. So example, find the volume of a solid obtained by rotating the region bound by y equals x to the fourth, y equals 16, and x equals 0 about the y-axis. Right, so once again, this problem is different. I invite you to, at the very least, try to sketch this thing and try to determine why this problem is different than the last one. So give that a shot. All right, well, hopefully you sketched y equals x to the fourth, and that pretty much looks like y equals x squared. Y equals 16, that's just horizontal line. And x equals 0. So let's see, I guess I have to be honest, I really didn't need this here. I'm going to cross that out because this guy is already bound within here, and we're going to rotate it around. So it looks like I even have the cross-section available. So with that in mind, let's sketch a typical cylinder. And how is this problem different? Well, hopefully you said, well, this problem is different because I'm stacking my pancakes or my cylinders this way instead of this way. In fact, the height of a given cylinder is no longer delta x, it's now delta y. So this is going to be an integral with respect to y. So I'm going to add these guys up as y goes from 0 to 16. I'm still going to need my pi r squared. We'll take care of that in a second. But the delta y is going to translate into dy when I convert my Riemann sum into the integral. So what is this radius? Well, this radius for a given y is, well, let's see. If y equals x to the fourth, then y to the fourth is equal to x. So for this y, if I want this length from here to here, I could just take y to the 1/4. That will give me that distance, and that will give me the radius. So this would be the integral that you need to look at. So the moral of the story is, if you are rotating on this axis around this way, you're in the world of dy. If you're rotating around this way, you're in the world of dx. So that's where we're rotating around the x-axis. Right, I want to give one final example, or one final group of examples. Same region, different axes that we're going to rotate about. So this one I'm going to sketch the region for you. And this is the region bound by y equals x and y equals x squared. So I want to do a couple of things with this region. So I want to, one, rotate about the x-axis. So let's see. If I rotate this region around the x-axis, then I'm going to have another region down here acting as my cross-section. And this region, or this solid, is different than the ones we've talked about already. So pause the video for a second. What's different about this solid revolution? So hopefully you said that this guy's got some space in here. So when we rotate it around, you could think of it as having a vase that we can actually put stuff into. So how are we going to get this volume? Well, what we're going to do is we're going to compute the whole thing, and then we can just subtract out, the inside. So we'll take the entire solid and subtract out that whole. So that sounds like we need two integrals. And by my picture, this guy is going to be in terms of x's, because these guys are delta x. Okay, so let's start mapping this out. Well, first off, where is this going to start and where is this going to end? We need to know where x equals x squared. So you might be able to solve that in your head. If not, we could see it's going to happen at 0, 1. So we need pi times the radius that we have to figure out. So let's write that, dx, minus the inside guy. Again, we'll figure this stuff out in a second, but I like to have the overall structure of the integral first. All right, well, at this point, I would recommend pausing the video, seeing if you can come up with the radius of that guy and the radius of that guy. Hopefully you said that the radius of the first one is just x. So for a given x, I need to spit out the y. For a given x, I need to spit out the y, and y equals x. So it'll just be pi times x squared. For the second one, I need this distance. For a given x, I need that distance. Well, that's just going to be x squared. Because for a given x, y is equal to x squared. So that would be that integral. Okay, so I'm going to take the same region and do another type of rotation. So same game. Now what I want to do is I want to rotate this guy about the y-axis. So I'm going to rotate it this way. So you actually have all the tools to solve this problem. I would recommend pausing the video and giving it a shot. Okay, so hopefully what you did is you first drew the other part of this. Again, it's going to be an outer minus inner problem. So an outer cylinder might look like this. We're going to subtract out an inner cylinder. So I'm going to have two integrals. And hopefully you guys realize that this is a dy problem because the heights of the ith cylinder is delta y, stacking them this way. Okay, so I need two of these guys. The y values also go from 0 to 1. The y values also go from 0 to 1. So we have pi something squared dy minus the integral from 0 to 1 of pi something squared dy. for a given y value, this distance is what? Well, y equals x squared, so the square root of that y will give me the x value. So therefore, this guy is going to be the square root of y. I'm then going to subtract out this distance. Well, I want to subtract this out. For a given y, as I move this way, I need that x value, but y is equal to x. So this is just going to be y squared over here. So let me mention a couple of things before we do the final example. Every single one of these you have to draw. There's no way that you can solve these without drawing them. Okay, none of them are what we would call cookie cutter problems. Second, a tip, make sure that if you have a dy here, that this guy is y stuff. So you should never have dy and x or dx and y. So that's a big typo that I see time and time again. All right, let's do a third problem with the same region and a different axis of rotation. So same region, so let me sketch this guy. So here's 0, here's 1. Now I want to rotate about the line x equals 2. So this is always the most challenging one for students, kind of this rotation out of nowhere. You actually have all the tools to solve it, so I would recommend giving this one a shot, spending a couple minutes trying to solve it. All right, so let's see. The first thing I'm going to do is I'm going to imagine rotating this around. So when I rotate it around, I should have something that's a mirror image on the other side. This problem is different than other problems in the sense that this quote-unquote solid is going to have this gaping hole in there because when I rotate it around, it's kind of a weird shaped tube. But we can still approach it the same way. So what I'm going to do is I'm going to take the outer cylinder, and I'm once again going to subtract out this inner cylinder to solve the problem. This is a dy problem, delta y. My y's go from 0 to 1, and I'm going to have a subtraction. So once again, let me first create the structure. And then I'll fill in the details. Okay, so let's see. I need to find this distance because that is the radius of the cylinder. For a given y, I need this distance. Now, since y equals x, I know that this distance is just y because y equals x. I want this distance. I know this whole distance is 2, so I guess I could take 2 minus y, and that'll give me the radius that I'm interested in. You might want to rewind and play that back. That's definitely notoriously challenging for students, so think about that. And once you feel confident about that, pause the video yet again and give the second one a shot. All right, hopefully you said for this one, this whole distance is 2, so I'm trying to find this radius. That whole distance is 2. X equals the square root of y, so this distance is the square root of y. Therefore, this will be 2 minus the square root of y quantity squared. All right, that's all I have to say about solids of revolution, finding their volumes. The key to success with these guys is to draw the picture and draw some typical cylinders so that you can see what's going on. All right, thanks for listening.